A house that inflates itself in minutes. A 300-ton bridge sliding across a valley as if weightless. Concrete that can heal its own cracks. These are not science fiction. They are breakthrough construction methods so advanced that even world leaders couldn't believe their eyes. But there is a hidden race behind these genius techniques. Whoever masters speed and precision will rewrite how our cities rise. The question is, what is pushing construction into impossible territory, and which innovations could change the way we build forever? In 1975, a warehouse collapse in Idaho set an engineer named David South on a mission. The disaster exposed the limits of traditional truss roofs, heavy, slow to build, and vulnerable under stress. South's answer looked nothing like conventional construction. He designed a fabric airform shaped to the final building, anchored it to a concrete ring, and fired up a blower. In just 20 minutes, the airform expanded into a perfect dome, held aloft by nothing but air pressure. The process was so unfamiliar that local building officials doubted it could even stand, let alone meet code. South gambled everything, his savings and his reputation, on the idea that air could replace tons of wooden scaffolds and molds. Once inflated, a crew sprayed polyurethane foam on the inside, creating a seamless layer of insulation. The foam, with an R value around 6 to 7 per inch, locked in heat and formed a base for the next step. Steel rebar was pressed into the fresh foam, then shotcrete, which is high-strength concrete, was sprayed over the mesh. The shell cured in just 8 to 12 hours, while the airform kept its shape. By the next day, the structure was self-supporting, weatherproof, and ready for finishing. The airform stayed put, doubling as a permanent waterproof membrane. Getting approval was not easy. Inspectors demanded repeated demonstrations and third-party engineering reports. South's domes had to prove they could withstand wind, fire, and even earthquakes. But the results were undeniable. A disaster-proof building finished in days instead of months, with no need for heavy wood or steel formwork. The secret was not brute force. It was precise control of geometry and pressure, turning a risky experiment into a new standard for speed and resilience. Steel bridge segments, each weighing over 300 tons, wait on the assembly ground behind a concrete abutment. Hydraulic jacks, capable of pushing with forces up to 1,000 kilonewtons, press against the rear of the span. At the front, a launch nose made from lighter steel truss stretches ahead to guide the segment over the first pier. Everything rests on pads coated with PTFE, known as Teflon. The friction coefficient is just 0.05. That means thousands of tons can glide forward with the force of a single truck engine. Engineers monitor every millimeter. Laser sensors track deck alignment, while strain gauges and inclinometers feed real-time data to the control room. The push begins. At a steady 10 meters per hour, the segment slides out over the void. The launch nose flexes as it cantilevers, transferring weight smoothly onto the next pier. This is incremental launching, no scaffolds, no cranes over the valley. Just pure geometric control and mechanical force. The process runs through the night under floodlights and the watchful eyes of dignitaries and media. Every movement is scrutinized. A misstep could jam the pads or twist the deck, risking months of delay and a very public failure. For the bridge engineer, every sensor ping and hydraulic pulse is a heartbeat. By dawn, the span is in place, aligned to within a few millimeters, ready for the next segment. The spectacle is not just the weight moved, but the precision and calm under pressure, witnessed by politicians and broadcast across the country. A gantry moves into position at the edge of a bare concrete slab. Instead of a human crew, a robotic arm swings into action, guided by a digital blueprint. This is 3D printed construction. Layer by layer, a house takes shape with almost no manual labor. In Dubai, Apis Core's mobile printer completed a 31 square meter office in less than 24 hours. The nozzle lays down ribbons of fast-setting concrete, each layer just 300 microns thick. Cameras and sensors track every pass, correcting in real time to keep tolerances tight, within a couple of millimeters. even as temperatures shift and mix consistency changes. Operators tune the concrete recipe on the fly, balancing set time and flow. The mix must hold its shape instantly, but still bond perfectly to the layer below. Rheology, the science of flow, matters more than brute strength. If the concrete is too stiff, the print head jams or the wall cracks. Too runny, and the structure sags before it cures. Each adjustment is logged and checked by an automated quality control system. By morning, the walls are done. There is no scaffolding, no wasted material, no trades waiting for their turn. Officials walk through the finished shell, inspecting the result. The process is so fast and precise that it is already drawing interest from city planners and housing agencies. API's Core and Cobod, two of the field's leaders, report similar results worldwide: 24-hour builds, minimal crew, and a new standard for speed. In the world of construction, automation is not a future promise. It is a present reality, measured in hours, not months. Geometry, not brute force, governs how a structure stands or falls. In engineering, curves are more than decoration. They are the secret to strength. A thin shell, doubly curved like an eggshell or a dome, can carry loads that would crush a flat slab of the same thickness. This is Gaussian curvature at work. The more a surface bends in two directions, the more it resists buckling and collapse. For a shell, the ratio of span to thickness, often called the R to S ratio, can be extreme. Some modern domes span 30 meters with shells less than 100 millimeters thick, holding their shape against wind, snow, and even earthquakes. Precision is everything. On a geodesic grid, each triangle or hexagon must meet its neighbors within a tolerance of less than 3 millimeters. Any error multiplies as the structure grows, risking a cascade of stress and possible failure. Engineers use algorithms to optimize the placement of every node and strut, balancing forces so that the entire grid carries load as a unified whole. This mathematical choreography allows for lightweight frames that seem to float, yet can support tons of glass, steel, or concrete. The same principles drive the design of bridge arches and shells. By shaping the path of force, a thin arch can hold up a highway, while a flat beam would bend or snap. The famous Maillart bridges in Switzerland used concrete shells so thin they were once dismissed as impossible, until decades of service proved otherwise. Today, digital modeling and laser scanning let builders push these limits further. On site, sensors track every shift in alignment and every fraction of a degree in curvature. Adjustments are made in real time, ensuring that theory matches reality. These advances are not just academic. They make possible the rapid, material-efficient construction seen in inflatable domes, launched bridges, and even robotic formwork. By mastering geometry, engineers turn ordinary materials into extraordinary structures. Proof that, in construction, the right shape can be stronger than sheer mass. A wall of glass stretches toward Lake Michigan, then begins to move. At the Milwaukee Art Museum, the building's Brise Soleil, two enormous steel wings, unfolds across the sky. Each cycle draws over 2 kilowatt-hours, yet the payoff is daylight transformed and a sculptural presence that stops visitors in their tracks. Architect Santiago Calatrava described it as a new way for architecture to breathe, not just shelter. Sensors and hydraulic actuators coordinate every motion, opening and closing the wings in response to sun and wind. It's not just spectacle. The wings reduce glare and heat, protecting priceless art while saving energy. Across the world, kinetic facades are turning static buildings into dynamic machines. In Yeosu, South Korea, the One Ocean Pavilion's exterior ripples with hundreds of motorized panels. Each panel tilts and rotates, programmed by control logic that reads sunlight and weather conditions. The result is a facade that adapts minute by minute, shading interiors and cutting cooling loads without blocking views. The Bund Finance Center in Shanghai takes a different approach. Its moving veil of stainless steel tubes slides along rails, shifting from transparent to opaque. The entire curtain, inspired by traditional Chinese theater, can enclose or reveal the building in under 5 minutes, creating a stage for public events and controlling solar gain for offices inside. Abu Dhabi's Al Bar Towers push the idea further. More than 2,000 origami-like screens, each driven by a servo actuator, bloom open as the sun rises and fold shut at dusk. The system slashes solar heat by half, and the geometry is rooted in the ancient Mashrabiya latticework of the Middle East. Engineers faced setbacks. Early prototypes suffered actuator fatigue and delays, but the team preserved the intricate pattern, fusing heritage with advanced automation. One designer called it a building that responds like a living organism. In Tehran, the Sharifiha house reimagines the boundary between inside and out. Entire rooms, mounted on electric turntables, rotate 90 degrees in just a minute and a half. Residents can open their living spaces to sunlight and fresh air, or seal them for privacy and comfort. Architect Alireza Tagaboni notes that the ability to reshape space on demand has changed how families live. Flexibility is built into the walls themselves. These buildings don't just stand against the elements, they move with them. Geometry, sensors, and actuators combine to make structures that adapt, save energy, and surprise. But every moving part demands new materials and precision, setting the stage for breakthroughs in construction science. Concrete that glows after dark owes its light to strontium aluminate crystals. These phosphorescent aggregates absorb sunlight by day and slowly release it at night, keeping paths and walls visible for 8 hours. No wires, no bulbs. The effect is strongest in the first 2 years, and then it fades as weather wears the surface. But for public spaces, it means built-in, maintenance-free illumination. Self-healing. Concrete takes a cue from biology. Bacterial spores, dormant for up to 200 years, are mixed into the concrete. When water seeps into a crack, the spores reactivate, feed on nutrients, and produce limestone, sealing microcracks up to 0.5 millimeter wide within days. It will not mend major fractures, but it dramatically reduces repair needs and extends the lifespan of bridges and tunnels. Aerogel insulation is mostly air, over 95%, yet it outperforms traditional materials. With a density as low as 0.15 grams per cubic centimeter, a thin aerogel panel can stop a blowtorch from melting chocolate just inches away. NASA relies on it for Mars missions, and architects use it to create ultra-thin, highly efficient walls. Robotic knitting machines now shape concrete in ways timber molds never could. Custom textile forms are woven, sprayed with concrete, and left to harden, minimizing waste and enabling complex curves. Each breakthrough began in the lab, but now these techniques shape structures built for the world's toughest conditions. Offshore, where waves reach as high as city buses and winds hammer with hurricane force, engineers anchor floating wind turbines using mooring lines that each withstand over 3 million newtons of tension. This is enough to hold more than 300 tons. These platforms do not rest on the seabed. Instead, they float, tethered by triple redundant anchors. If one line fails in a storm, the others keep the turbine upright and generating, buying time for emergency repairs. Hywind Scotland's turbines, for example, use 3-point catenary moorings, each designed to survive the worst North Atlantic weather. Dynamic simulations predict every possible movement, pitch, roll, and surge so that the turbines keep spinning and cables stay intact, even as the sea heaves beneath them. On land threatened by water, the approach flips, and homes rise to meet the flood. In southern Louisiana, amphibious foundations allow entire houses to float upward on guideposts when rivers spill their banks. These guideposts are engineered for vertical travel up to 3 meters, keeping the house perfectly aligned as it lifts and settles. After the water recedes, the structure returns to its original position, with less than 4 centimeters of drift, tested in real flood events. Homeowners describe the relief of watching their houses rise with the storm instead of fighting against it. These systems rely on buoyancy and precision rails, not brute strength, offering a lifeline in places where traditional elevation is too costly or disruptive. Whether out at sea or in flood zones, These designs show how engineering adapts to environments that defeat conventional building. Floating wind farms and amphibious homes are not just technical marvels, they are frontline defenses against a world where water no longer stays where it is supposed to. A bricklaying robot hums along a scaffold, placing up to 3,000 bricks per hour, each one set with a tolerance tighter than 2 millimeters. The machine does not pause for lunch or shift changes. It works from a digital blueprint, guided by laser sensors and real-time feedback. 2 operators manage the setup and material feed, replacing what would normally be a crew of masons. The robot's cycle is relentless. Pick, butter, place, repeat. Wall after wall, floor after floor. On large projects, this pace means a single robot can match the daily output of 6 skilled workers. Automation is not limited to the horizontal. In dense city centers, top-down construction flips the old sequence. After pouring a ground-level slab and setting perimeter walls, crews start building upward and downward at the same time. While one team assembles the tower's core above, another excavates the basement below, both supported by columns threaded through the initial slab. Temporary steel braces stabilize the site until permanent walls are in place. The overlap reduces project timelines by up to 50%. Where a high-rise once took years, the structure can now be enclosed in months, minimizing street disruption and noise. For cities where every week counts and every meter is contested, these methods turn construction into a continuous, orchestrated process day and night, above and below ground. A hillside home disappears beneath a blanket of earth, its roof barely visible among wild grasses. This is earth bermid construction, a method as old as farming, now refined with modern engineering. The structure's shell, designed for strength, is buried under layers of soil and vegetation. The result, insulation values that reach R60 or higher, far beyond what standard walls can achieve. Inside, the temperature barely shifts, even as seasons change. Local builders use advanced moisture barriers and precision air handling to keep these spaces dry and comfortable. Fire, wind, and noise are tamed by the mass overhead, creating a silent, storm-proof retreat. On another site, a mechanized rammer thunders against plywood forms, compressing soil into dense, stone-hard walls. Modern rammed earth construction, powered by piston-driven machines, achieves compressive strengths over 8 megapascals, matching or exceeding concrete block. Thermal modeling confirms these walls store heat by day and release it at night, reducing energy use. The process is fast. A small crew can raise entire walls in days, not weeks. In the factory, modular building sections move down an assembly line. Roofs, floors, and walls are cast, cured, and finished under controlled conditions, then shipped to site for rapid assembly. Factory managers track cycle times and quality, pushing throughput to dozens of modules per day. These methods revive ancient wisdom, using earth, mass, and geometry, while harnessing today's machines to deliver strength and sustainability at scale. Around the world, construction breakthroughs are being matched directly to urgent needs. The United Nations estimates that closing the global housing gap would require building 96,000 new homes every single day. Techniques like 3D printing and modular assembly are designed to scale. Factories and robots can work around the clock, but only if local codes and approvals keep pace. In flood-prone Louisiana, amphibious homes now rise and settle on precision guide rails, tested to return within 4 centimeters of their original position after real floods. Homeowners describe the sense of relief as water lifts their house instead of destroying it. Energy costs are falling too. Adaptive facades, like those on Al-Bar Towers, have cut solar heat gain by 50%, slashing cooling bills in some of the world's hottest cities. Yet every advance comes with caveats. Self-healing concrete can only seal small cracks, not major structural failures. Aerogel insulation remains expensive and fragile. Engineers point to regulatory slowdowns, insurance hurdles, and the challenge of training crews for new systems. As one engineer put it, "We can build faster and smarter, but the world has to agree on what counts as safe. Every day, cities add 200,000 new residents, demanding solutions that did not exist a decade ago. These construction breakthroughs are not just marvels. They are a response to real crises, from housing to climate resilience. As the world's needs accelerate, engineering will decide what is possible or impossible. The blueprints of today are fast becoming the foundations of tomorrow. What would you want built next? Let us know in the comments.